Okay. If there is no other comments or questions, maybe we can just move on to the next presentation. Okay, our next presenter is Colonel Alpaslan Tatlisuluoglu from the Turkish Navy. He's going to present. Actually, he's going to do two presentations, one after another. They are the part of his PhD thesis, and his first presentation is pressure measurements of an underwater detonation in sea. Okay, please go ahead.
Thank you, sir. This is Navy Captain Alpaslan Tatlisuluoglu. I'm working in Turkish Navy Underwater Search and Rescue Command. Now I load my presentation. Here is my presentation. Blast pressure measurement of an underwater detonation in sea. In an underwater detonation, the formation of superheated and highly compressed gas bubble around the charge causes the tremendous pressure increase, which in turn gives rise to shock wave. The spherically propagating shock wave initially has a speed much faster than that of sound in water and steep from with a sharp peak pressure value well above the acoustic pressure levels, which decays in approximately exponential fashion. We try to conduct open sea detonation measurement, but firstly, I try to explain the underwater explosion area. The explosive, chemically unstable substance is triggered into a chemical reaction which results in the explosion. The unstable substance is converted into a stable gas at a very high temperature, approximately 3000 Celsius, and pressure 50,000 atmosphere. Almost instantaneous rise of pressure to a peak value in the superheated gas generates a compression wave with a steep wall-like front end exponentially decaying back, propagating radially. This is called the shock wave, and it is the most destructive one amongst a series of pulses generated by an underwater explosions. Here is the general formula describing the size of shock wave. It was first declared by Dr. Robert Cole more than 60 years ago. We try to set underwater explosion field measurements, and underwater pressure measurements were carried out during a planned open sea underwater detonation. Time histories of pressure charges in water were recorded at 8 stations placed at different locations. Evaluating of measurements and use of peak pressure values for redetermining the coefficients of the empirical power law approximation. An underwater detonation with 8 pressure gauges mounted on a suspended steel frame in the seawater was carried out. A cylindrical explosive of 25 kilogram TNT equivalent was detonated in the Sea of Marmara. The charge is under 18-meter depth. The time histories of issuing pressure variations were recorded by non-resonant high voltage output PCB series pressure sensors, an L-shaped steel frame suspended by buoyant spheres was used to hold the pressure gauges at different positions as on the screen. Shockwave was measured. These values is the most important parameter for assessing the potential damage to a sea structure. Therefore, special attention is paid to this value and its prediction. Here are the graphics presenting the measured peak pressure values and the corresponding distance from the charge for all the gauges. Time is defined in milliseconds. Pressure is defined in megapascals. Gauge 2 and 6. Gauge 8 and 3. Gauge 7 and 4. The peak or maximum pressure and decay time, theta, would obviously depend on the quantity of charge and the distance from this charge at which the observation is done. Our aim is to redefine tuning parameters, which are screened on the screen A and B. Using the measured data given in table before, the coefficients in equation are determined by the method of least squares. Following the usual approach, first we take the natural logarithm of equation. Then we obtain x and y datas. After that, we set the x and y datas. We obtain linearization and we got new tuning parameters. We can see these values are slightly different from the solutions obtained from the usual approach given by Dr. Cole. Visually, only minor differences can be observed. However, comparisons with measurements for each pair revealed clearly that the error minimization done by direct use of power function results in the least errors for the data point used. Here are the results: direct, measured, logarithmic, and standard. Conclusion: blast pressure measurement records of controlled underwater explosion in the sea are conducted. All 8 gauges were exposed to shock wave just in about 1.8 milliseconds. Since actual sea trials are rare, these records are expected to be quite useful for testing the relevant numerical simulations. Parameters of the semi-empirical maximum pressure formula are determined by use of field data via 2 different formulations of the error function. Calculated coefficients show slight variation depending on the specific error function, but agree fairly well with the generally accepted values. This agreement serves as a further assurance for the accuracy of measurements. Thank you. I'm ready to answer your questions and comments.
Thank you, Colonel Tatlisuluoglu. I think this was also important because just like the first presentation, this also has own importance because the field measurements, especially for underwater detonations, as far as I know, are very rare, and most of the times they are not revealed because of the confidence reasons. They don't give away the measured data. This was one of the really rare instances, let's say, that we are able to confirm and reveal the actual field data for the underwater blast measurements. Thank you. Okay, are there any questions?
I have just a comment.
Please.
As far as I know, thank you for your presentation, by the way. As far as I know, underwater explosion is a very hot topic, especially in the military applications. I'm very excited about to see your future studies. I just want to comment on that. Thank you.
Thank you very much.
Dear Chairman, I will give a comment. Thank you. Underwater acoustics in the still water and also in waves, I think both are interesting. For the experimental studies, of course, explosions and so on, you will need larger area and security and so on. You should you should prepare the experimental facility. But our facilities in Istanbul Technical University and Yıldız Technical University, we have a wave tank. I hope you can set an experimental setup and investigate the acoustics in waves.
Sir, it is my honor to have a chance to do experiments with that facility. I hope I try to do my best because there are more area to investigate and analyze. I know that. I try my best. Thank you.
Yes, thank you for all these comments. And any more? Is there anything more? No? Okay, now I think we can move to the next presentation. It is a continuation of the present work, actually. It is about the numerical simulations of shock wave effects on a ship-like form. Now, again, our presenter is Colonel Tatlisuluoglu. Yes.
Thank you very much, sir. I am Alpaslan Tatlisuluoglu. I am Navy captain. I work in Turkish Navy Underwater Search and Rescue Command. It's my honor to present this topic. Numerical simulation of shockwave effects on ship-like form. Firstly, I want to show you footage from USS Gerald R. Ford's first explosive event of full ship shock trials. It was conducted on Atlantic Ocean on June 18th, 2021.
We don't see anything on the screen.
Yes, can you share the screen, please?
Sorry.
Yes, it's okay.
Okay now.